nonetheless. Here we go. 3, 2, 1. Three, two, one, go. This is Retrace, segment number 77. We're live. This is Sunday, December 11th, 2022. And it is 10 p.m. Eastern, 7 p.m. Pacific. We're doing a double header today. Why? Because things need to get done. We're getting them done. Retrace is about what's going on out there. The short answer to that is computer control. The long answer to that is not going to happen right now. We got to be quick here. What we're going to do is do a recap video of Retrace segments 65 through 69, table-driven agent, 5-part series. Do an overview. Put this at the front of a playlist to make it easier for people to decide how deeply to go into the topic. Let's go deeply. Here we go. These are the notes that we're going to work from, and we're just going to kind of go through as you would. We've got it all here in front of us. So we started, first of all, let's talk a little bit of context. The table-driven agent comes from AIMA4e, Artificial Intelligence Modern Approach, Russell and Norvig, 4th edition. This is page 48. We're in the December to Remember Math and Code event, preparing for our 6-month deep dive study of this text from January to June inclusive of 2023. So we're spending December tackling the hard parts, making sure that nothing bogs us down in that time period next year. It's not even it's 3 weeks away. So page 48 is where the first real math and code appear, and that's why we chose table-driven agent. Okay. So in in part number 1, Re65, segment Re65, we had already done also I should say, for AIMA4e, we did a companion in the lead up to this. We did an overview of the whole book. And so you can read through the companion at AIMA4e.retrace.com. That'll land your plane right where we are with Re65. Okay, we talked about agents a little bit, the different kinds, table-driven reflex, model-based reflex, goal-based, utility-based learning. But we're talking about table-driven, just the simplest version that we tackle first. And intelligent agents can be thought of more broadly than just computer programs. But here we're just talking computer programs. Here's the code, the pseudocode from the book. Inputs are percept and table. Output is action for each loop through this function. This is a function. This is not in a particular programming language. It's a function in their pseudocode language that's meant to be implemented in, you guessed it, an actual programming language. This is their Python implementation. We're not going to end up using this code. We're going to use little snippets of it later on because this is not quite suitable for our purposes. But this conveys the same idea. You can get to these things from aima.cs.berkeley.edu/algorithms and their GitHub page, and AIMA4e.retrace.com, AIMA4e.retrace.com will get you there. Links.retrace.com will get you to the official AIMA stuff as well. Here we talked about defining some terms. We're going to talk again about them in Re66 in just a second here. But things like program or the different kinds of function, basically, we're sort of, will lend you to confusion. So computer programming function is different from an agent function and mathematical function, but we do a better job of defining those in the next segment. Just keep in mind that agent functions and agent programs are separate. The agent program is the whole thing, and the agent function is just the table part in this case. This is the part that makes it smart, or smarter than average, or is intended to make it smart. But this is the whole program that's not necessarily smart, or as smart as we want it to be. And you can think of the agent architecture as being so the agent is the architecture, which is the hardware, plus the program, which is the software. Think body and brain, maybe. That's one way of thinking of it. And that memory is represented by the pseudocode variable persistent in the AIMA4e pseudocode. Okay, that's Re65. In Re66, we tweaked the terminology. We talked about initializing memory objects and what a dictionary is in Python and what a memory object is. And these other things I brought in sort of from Althoff. You can go into the notes if you care about that. Computer program function, okay, a software input-output machine. Mathematical function, a relation between two sets. And an intelligent agent function, the input-output, percept action table, or whatever, that makes a dumb program smart. And so we go a little bit into what we mean by that. But that's a bit in the weeds for this segment. And then we work the table-driven agent code. And by the end of the segment, we're talking about always be coding. It feels like the right thing to do, although I would add always be mathing. ABM is probably going to come up at some point. Here's the code. So again, the pseudocode, same thing. Here I've highlighted the corresponding objects over here in in their Python implementation. But then we have 3 boxes here that all represent running code that implements this agent program, especially the agent function. So an implementation of the agent program is the whole thing. And I mean, this is an interactive shell, so this isn't a single file. You could put this in a file, but we did it interactively in the segment to make it clear what was going on. So implementing the whole agent program is each one of these 3 whole boxes. Implementing the agent function is the same in each one because it's just the table. What do we mean by that? Well, basically, we're going to get a percept. We're talking about a computer program, artificial intelligence agent program that's just running in a computer. So its whole world is input-output in the form of whatever data we can send to it, and it lives inside of a computer. So its whole world. So it never sees the color red, but we can send it the word red, the string RED. That's what we do here. Oh, we don't do it here. So this is the table that interprets when it receives the string red. It sends back a thumbs up. It doesn't actually put its thumbs up. It just sends back text because this is a very simplified agent, because we're trying to learn how they work, not make one that's really for sale at Target. Okay, so we put the agent function, this table that says, okay, if your history of percepts is just 1 percept, give a thumbs up, and it's red, give a thumbs up. If the history of your percepts is 2 reds, act like you're interested. If the history of your percepts is 2 reds and a green, continue to act like you're interested. And if your history of percepts is red, red, green, red, ooh, that's not good. You should definitely vote that one down. And then we go through here, line by line, in this first box, doing what I just described, and we end up there. You can do it more easily if you write up several of those lines as a program, and then you just send percepts to the program instead of manually appending the percept history list. This is a percept list history. That's the thing that gets checked. And then the table is where the lookup happens to get the action. Every time the agent gets a percept, it takes its list, looks up that list in the table that we've specified, and gives back an action. Same results, same output here. Different agent program, same agent function, and same agent behavior. Finally, here we do it even more fancy. We use the code that's very similar to the way that AIMA4e Python implementation looks, except we had to modify it so that we could pass the table, the percepts, and the percept list from the outside, so it was a single function. Same thing here, same output. Okay, that's the code, and again, always be coding, always be coding. Okay, let's go to Retraice segment number 67. This is part 3. We want to talk about the limits of this table. This table-driven agent has mathematical limits. The way we describe those mathematical limits is this expression here. This is summation notation. It's saying the sum from 1 to the number of percepts in the lifetime of the agent. You would add the number of possible percepts in the world of the agent raised to the number of percepts it has received so far. That's what that means. That I've explained that in many different words and different arrangements below. And the key to, you just have to get used to this and spend some time thinking about what does it mean. So first of all, if you expand this fancy and you get rid of the summation notation, you're going to have to write this right-hand part. The blue P, the bars represent the number of elements in the set. The P represents the set. So our set has only 2 elements, red and green, and the P represents the set red and green, but the bars around it represent the number 2, which is the number of elements in that set. We write it the long way without summation notation. It looks like this. How long is the agent's life? Well, in our agent's life, we're only going to have 4 percepts in its whole history. So this is going to have 4 terms. We plug in the actual numbers for our 2 percept world and a 4 percept lifetime for the agent. How many entries do we need in our table? 30. Wow. What a disappointment. Our table only covered 4 out of the 30 possible percepts. If we wanted to completely specify an action, if we wanted to specify an action for every single possible percept history that our simple little agent was going to could experience in its 4 percept lifetime, it would have had to be 30 entries long. Now you can write an if-then-else agent program that handles it. Says, okay, if you get these percepts, do this. Otherwise, just do nothing and go ask for another percept or wait for another percept. So doing nothing in a category is a response to a large swath of the possible table entries or would-be table entries is an option, but we didn't do the math on that. We're talking about the limits of this agent. We're not talking about ways to work around those limits or work within those limits. Here, we talk about the combinatorial explosion. Where does the explosion happen? It happens on this last term. Okay, this is essentially an exponential. It is an exponential function because every step we take, this number goes up. Okay, so we're taking steps along an x-axis that we don't have drawn here. That x-axis is plugged into this exponent. It's raised 2 to the 4, then 2 to the 5, then 2 to the 6. That's 2 to the x. F of x equals 2 to the x equals big for all values of above, say, x equals 14, which is roughly 16,000. If you have a 3-percept world and you take 14 percepts, i.e. 14 steps in your agent's lifetime before it dies, you, on the last, this is the size of that percept history is like twice this. It's like 8 million. But on the last step, you double the size, more than double, actually. It's more like 2 or 3 million. I can't remember. I think I do the math on the next one. The point is, every step you take, you're blowing up the table, okay? That's what this is all about. I also said down here in, I think I say it in Retraice 68, but I wrote it in response to this one. When I say like, that AI code is, it takes an imprecise answer and improves it, as opposed to classical algorithms or classical code that capture the steps to arrive at a precise answer. That's only really if you equate artificial intelligence code with machine learning code. So I kind of qualify and correct myself here, and then I talk about it again in Re78 at the top, amendment to Re68. Oh, and also I kept saying sequence instead of series. A sequence is the elements in our list. So red, let's say we have a list of 2, 4, 6, 8, 10, 12. That's a sequence. You add those together, then it's a series. Okay, now sometimes the series is infinite, sometimes it's finite. Same thing with a sequence; they can both be infinite or finite. But I just kept saying it wrong, and it was, or I said it wrong once or twice, and it drives me crazy. I think I did the same thing with equation and expression. Let's get this right. I should not be your mathematician, but I can still help, and I try very hard to get the right answer. This is an expression. The equal sign. This is, maybe you call it a little equation in here, but really this is just this is almost setting t equal to, but this is not an equation because there aren't two expressions on either side of an equal sign, okay? This is an expression. You put an equal sign here and you put a number over here or some other algebra, and then you're saying these are two things are equal. That's an equation. Get it right. Don't be like me. Be like better. Okay, warnings about Python. I talked about, probably shouldn't have put this in here, but it just came out that way. Enveloping and environmenting your Python installation and also all of your Python packages, modules. What's the other one? Modules and not submodules, modules and I don't know, but there are different terms for just basically more Python code that you didn't write that you want to import to your code. I give some links and stuff how to deal with that, and I talk about Docker, which is sort of the more scaled up version of that, dealing with containers generally, not just Python. Python's a great language, but it's moving so fast that you need to really sort of wrap it up in a container to keep your code today working years from now, and avoiding dependency hell. Okay, here we bring it all together. We bring together the math that we've already done, and we say, look, we want to write some Python code that actually does this math for us. We don't want to be manually calculating an exponential explosion like this, a combinatorial explosion. And here's how you do it. Print series takes the number of percepts that are going to be that are in the world of your agent, and then the lifetime of your agent. In our case, we had 2 percepts in the world, red and green. It's going to have a 4-step lifetime. So this is 2 and 4. You see these down here, 2 and 4. And then it does some magic. It says for I in range, and then you go from 2 to lifetime. You have to do some fence posting things here to, you'd think you'd start with 1, but you just don't. Trust me. I mean, it's just a lot of math and a lot of code has fence posting problems. If you're not familiar with those, Google them. Update the series value, and then by the end of this loop, you have a final number for the series, and it's 30, and it matches. And the more you test this, the more you start to trust this code is getting the right answer. Okay, that's the end of 68. 69, we just sort of took a look backward. Well, first of all, we resisted the temptation to go into all the cool stuff, agent-oriented programming, agent-oriented software engineering, all this other stuff that's coming up around the table-driven agent and thinking about how to make progress. So how do you go do something useful with this tool that you just learned and started to understand? But we're resisting that temptation because we have things to do, and that's why we're doing a doubleheader tonight, and that's why we cut this off at the knees, even though I very much would have liked to talk about agent-oriented software engineering, which is, according to its original theorist, his name Shoham, is a subset of object-oriented software engineering, agent-oriented. It's just fascinating to me, but I don't know much about it. But I love everything I've read. And autonomic computing is part. Okay, see. I'm falling off the boat. Get back in. ECMP is the methodology that we decided is represented by the first 4 segments on the table-driven agent. We start in English, including pseudocode. We want to comprehend the problems and solutions, and then get out of English into code. That's the next phase. Implement electron-based machines to do work. Then get out of code and into math to figure out the trustworthiness and the limits of the machines, and then go out in the world and go do something useful. ECMP. You don't have to do it in that order. You might do it in reverse. You might mix it up. Doesn't matter. But, the table-driven agent is a new tool. It's a hammer looking for nails. Can we imagine things? I think in the footnotes here, I imagine launching missiles at people and then dropping pallets of food to refugees. So go check that out. Last but not least, what does a general mobilization look like in the age of AI? What is war going to look like? What does it already look like? Things to think about. There's more and more and more and more. Man, do not Google AI. Do not Google it. It's every day is more. Okay, so that's it. That's what we did with the table-driven agent. Check it out. All references for today's segment will be in the PDF notes. We will do some PDF notes to even distill what we've done so far. That'll be at our website, retraice.com, retraice.com. Next segment is in 43 minutes. We're doing a double header, and we're going to do a recap of segments Re70 to Re76, which were on partial derivatives and gradients in the context of pages 119 to 122, AIMA4e. Hope you enjoyed it. All right, signing off.